How fast is our universe expanding? First off, let's talk about the Hubble constant. This isn't just any number. It's the rate at which the universe is stretching out, bringing galaxies further apart. Named after the legendary astronomer Edwin Hubble, this constant measures the expansion speed per megaparsec. That's 1,000,000 parsecs, if you were wondering. Now, estimating this constant isn't straightforward. We have two main methods: local measurements, where we look at nearby galaxies and supernovae, and cosmic microwave background measurements, which involve peering back at light from the early universe. But here's where it gets interesting. These methods don't quite agree. Local measurements give us a Hubble constant of about 73 kilometers per second per megaparsec. On the other hand, those early universe measurements suggest something closer to 67. This discrepancy is what we call the Hubble tension, and it's a hot topic in astronomy today. Why does this matter, you might ask? Well, understanding the rate of expansion sheds light on the past, present, and future of our universe. In the past, right after the Big Bang, the universe was a hot, dense point. Knowing how fast the universe expands helps us figure out how old it is and what it was made of in those first moments. In the present, this expansion influences how we perceive distances in space. As the universe expands, light from distant galaxies stretches to longer wavelengths. This is the redshift that helps astronomers map the cosmos. And for the future, the fate of the universe hinges on this expansion. If it keeps speeding up, driven by the mysterious dark energy that makes up about 68% of the universe, we could end up in a big freeze. But if it slows down, we might face a big crunch where everything collapses back into a singularity. Speaking of dark energy, it's the wild card in our cosmic deck. This elusive force is pushing the universe to expand faster and faster, yet we know so little about it. Imagine a future where new technologies like the James Webb Space Telescope offer clearer insights, potentially solving the Hubble tension. Or where breakthroughs in physics provide new theories that explain dark energy, and maybe even quantum gravity. The universe is a grand, expanding mystery, and each discovery is a piece of the puzzle. Is space infinite? To tackle this, we need to distinguish between the observable universe and the entire universe. First, the observable universe. This is the region of space that we can see from Earth, limited by the speed of light and the age of the universe, which is approximately 13.8 billion years old. However, due to the universe's expansion, this observable bubble stretches about 46.5 billion light-years in every direction. But what lies beyond this bubble? The entire universe might be vastly larger, potentially infinite, though its total size remains one of the greatest unknowns in cosmology. Now let's consider the shape of the universe, which plays a crucial role in determining its finiteness or infiniteness. If the universe is perfectly flat, it could be infinite. Current measurements from the cosmic microwave background radiation suggest that our universe is very close to being flat, supporting the possibility of an infinite cosmos. On the other hand, if the universe is closed, like the surface of a sphere, it would be finite yet unbounded, meaning you could travel in one direction and eventually return to your starting point. Imagine it as a cosmic version of traveling around the Earth. Then there's the open universe with a saddle-like shape, which would be infinite and unbounded, expanding forever without looping back on itself. Various cosmological models and theories also provide insights into this enigma. According to the Big Bang model, the universe has been expanding since its inception. Whether this results in an infinite or finite cosmos depends on its shape and the total amount of matter and energy within it. Inflation theory, which posits a period of rapid expansion in the early universe, suggests that the observable universe might be just a small part of a much larger, potentially infinite whole. And then there are multiverse theories, which propose that our universe could be one of many, each with different properties, shapes, and sizes, some finite and others infinite. While the concept of an infinite universe is fascinating, it presents practical challenges. We can only observe and measure a finite portion of the cosmos, making it difficult to conclusively determine the universe's true extent. Moreover, the idea of infinity raises philosophical and theoretical questions that go beyond empirical science, touching on the nature of reality, space, and time itself. So is space truly infinite? The answer remains one of the most profound mysteries of our time. Let's turn our gaze to another age-old question that has captivated human curiosity for generations. Is there life in other galaxies? The question of whether there is life beyond our own galaxy is one of the most intriguing and fundamental questions in science. While we have not yet discovered definitive proof of extraterrestrial life, several lines of reasoning and scientific evidence suggest that it is possible, if not likely. First, consider the sheer scale of the universe. The observable universe contains an estimated 100 billion to 200 billion galaxies, each containing millions to billions of stars. This staggering number of stars and the planets orbiting them provides a vast number of opportunities for life to arise. To date, thousands of exoplanets, planets outside our solar system, have been discovered. Many of these are located in the habitable zone of their stars, where conditions might be right for liquid water to exist, a key ingredient for life as we know it. Next, let's consider the conditions necessary for life. For life to exist, certain conditions are generally considered necessary, such as the presence of water, an energy source, and a range of stable temperatures. Many exoplanets in our galaxy, the Milky Way, have been found to meet some of these criteria, suggesting that similar planets might exist in other galaxies. Additionally, the essential chemical elements for life, carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, are widespread throughout the universe. The processes that formed these elements are universal, meaning the basic building blocks for life are likely abundant in other galaxies as well. The Drake equation is a probabilistic formula used to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. While many of its variables are still uncertain, the equation highlights the factors that influence the likelihood of life, such as the rate of star formation and the fraction of stars with planets. If we apply the principles of the Drake equation to other galaxies, given the vast number of galaxies and stars, it becomes statistically plausible that many galaxies could host life. On Earth, life has been found in some of the most extreme environments, from deep-sea hydrothermal vents to acidic hot springs and the cold, dry valleys of Antarctica. The adaptability of life to such diverse conditions suggests that life could potentially thrive in a variety of environments elsewhere in the universe. The panspermia hypothesis suggests that life might spread through the universe via meteoroids, asteroids, and comets. This theory implies that life, once started, could potentially spread across galaxies. Current and future missions like the Mars rovers, Curiosity and Perseverance, the upcoming Europa Clipper mission, and the James Webb Space Telescope are designed to search for signs of life and habitable conditions beyond Earth. While these missions are focused within our solar system, their findings could provide insights applicable to other galaxies. SETI initiatives aim to detect signals from advanced civilizations. While efforts so far have not detected any definitive extraterrestrial signals, the search continues, expanding our understanding of the cosmos. Finally, we must consider the Fermi paradox, which highlights the apparent contradiction between the high probability of extraterrestrial civilizations and the lack of evidence for or contact with such civilizations. Various solutions to the paradox have been proposed, ranging from the rarity of intelligent life to the possibility that advanced civilizations are avoiding us or are simply too far away to detect. So, is there life in other galaxies? While we have yet to find definitive proof, the vastness of the universe and the adaptability of life suggest that the possibility is tantalizingly real. After delving into the mysteries of life in other galaxies, let's embark on a journey through one of the most captivating concepts in both science fiction and scientific inquiry: time travel. Is it possible to journey through time, and if so, how? Time travel has been a subject of fascination and speculation for decades. However, the scientific exploration of time travel involves complex theories in physics, particularly in the realms of general relativity and quantum mechanics. Here's an overview of the scientific perspectives on time travel. First, let's consider general relativity and time dilation. According to Einstein's theory of relativity, time dilation occurs when an object moves at speeds close to the speed of light or is in a strong gravitational field. For instance, an astronaut traveling at near light speed would experience time much more slowly compared to someone on Earth. This is a form of forward time travel. Similarly, in strong gravitational fields, such as near a black hole, time passes more slowly. This effect has been observed with precise clocks on GPS satellites, which need to account for both their speed and the weaker gravity at their altitude compared to Earth's surface. Next, let's delve into wormholes and closed time-like curves. Wormholes are theoretical tunnels in space-time that could, in principle, connect distant points in space and time. The concept, derived from general relativity, suggests that if traversable wormholes exist, they might allow for shortcuts through space-time, potentially enabling time travel. However, creating or stabilizing a wormhole would require exotic matter with negative energy density, which remains purely hypothetical. Solutions to Einstein's field equations, such as those involving rotating black holes, Kerr black holes, suggest the possibility of closed time-like curves where an object could theoretically return to its own past. These CTCs imply a form of backward time travel, but they raise numerous paradoxes and challenges, such as the famous grandfather paradox. Quantum mechanics also offers intriguing perspectives on time travel. Quantum entanglement introduces phenomena where particles remain interconnected, such that the state of one instantly influences the state of another, regardless of distance. While intriguing, entanglement does not provide a mechanism for time travel, but does suggest that our understanding of time could be more complex than classical physics suggests. Quantum tunneling allows particles to pass through barriers in ways that classical physics cannot explain. Some interpretations of quantum mechanics, like the many worlds interpretation, suggest that all possible outcomes of quantum events actually occur, potentially creating parallel timelines. This is speculative and does not offer a practical method for time travel. Despite these fascinating theories, there are significant practical and theoretical challenges to time travel. The energy required to manipulate space-time for time travel, such as creating and maintaining a wormhole, is beyond our current technological capabilities. It is also uncertain whether the required exotic matter with negative energy exists. Time travel theories also face significant challenges with paradoxes, such as the grandfather paradox, where a time traveler could potentially prevent their own existence. Various theories propose solutions such as self-consistency, where any actions taken by a time traveler were always part of history, or the many worlds interpretation, but these remain speculative. To date, there is no experimental evidence supporting the possibility of time travel. While time dilation effects are well documented and consistent with relativity, actual travel to the past or future, beyond the effects of time dilation, has not been observed. So is time travel possible? While current scientific theories provide tantalizing possibilities, the practical and theoretical challenges remain formidable.